Measurement of segments. Level 1. Geometry was initially used to solve problems involving measurements on the earth. The word geometry comes from the Greek word geo, which means earth, and metri, which means measure. So this is the mathematics that allows us to carry out measurements on the earth. Although the earth is essentially spherical in shape, when we view the earth in small regions, it appears to be flat. This is why in many practical situations where measurements are involved, the earth is assumed to be flat and considered to be part of a plane. You can think of a plane as a sheet of paper of points with no thickness, stretched tightly, and extending infinitely in all directions. Geometry that involves measurements in a plane is referred to as plane geometry. And in this course, the majority of the topics that we will cover will allow us to solve two-dimensional planar geometry problems. Later on in this course, we will use our new planar geometry knowledge and solve simple three-dimensional geometry problems. The field in geometry that deals with three-dimensional figures is known as solid geometry. In the following series of videos, we will learn how to measure line segments. In the previous video, we defined a line segment, also referred to as simply a segment, as a straight line that is made up of points that has a definite beginning and end. These 2 points are referred to as the endpoints of the segment. Because segments have a definite beginning and an end, they can be measured and have a unique length. We measure segments by using instruments such as rulers and meter sticks. We may use any convenient length as a unit of measure. Common units include inches, feet, yards, millimeters, centimeters, and meters. For example, segment AB measures 1 inch, and segment CD measures 5 centimeters. In geometry, the way we denote the measurement of a segment is by writing the endpoints of the segment. For example, the measurement of segment AB is 1 inch, and the measurement of segment CD is 5 centimeters. Notice the distinction between denoting a line segment, a geometric figure, and denoting the measurement or length of the line segment, which represents a numerical value. If you want to identify the line segment, we draw a horizontal segment, also known as a bar, on top of the letters. If we want to denote the measurement or length of the line segment, then we only denote the endpoints, and do not draw a horizontal segment or bar on top of the letters. We can also use a number line to find the measurement of a segment. The real number associated with a point on a line is called the coordinate of the point. For example, the following line segment is formed by point P and point Q, with point P located at the coordinate -4 and point Q located at the coordinate +2. Usually, only integers are labeled in a number line because it is impossible to label all the real numbers, like fractions or decimals, since there are infinite real numbers. The measurement of this line segment can be determined by measuring how far apart the endpoints are from one another. In other words, we measure the distance between the points. In this case, the measurement of segment PQ is 6. We can define the distance between point A and point B as a non-negative difference between their coordinates. For example, segment PQ can be found by subtracting the coordinates of the line segment. In this case, we can subtract -4 from +2, or subtract +2 from -4. Since we want the numbers to be non-negative, we take the absolute value of the result. In general, if a line segment has one endpoint located at the coordinate A and the second endpoint located at the coordinate B, then the length of the line segment is given by the absolute value of A minus B, or the absolute value of B minus A. Notice that we are not assigning a unit, such as inches or centimeters, to this length. When the unit is not explicitly stated, we can either leave our answer as a number, such as 6, or we can say that the line segment measures 6 units in length. Now let's talk about congruent segments. In geometry, two objects that have the same size and shape are called congruent. For many geometry figures, we can give a more precise definition of what it means to be congruent. Later on in this course, we will define congruent angles, congruent triangles, and congruent circles. Let's first define congruent segments. Congruent segments are segments that have the same lengths. In other words, the segments have equal measurements. In the figures shown, segments AB, CD, and EF are congruent. To indicate that segment AB and segment CD have equal lengths, or to denote that the distance from point A to point B equals the distance from point C to point D, we write AB equals CD, without using the line segment or bar symbol on top of the letters. To indicate that segment AB and segment CD are congruent, we use the following symbol. This symbol uses a tilde above the equal sign and is read as segment AB is congruent to segment CD. This statement can be used interchangeably, meaning that if segment AB is congruent to segment CD, then segment CD is congruent to segment AB. Remember to use equality for numbers and congruence for geometric figures. We can also use identical tick marks to indicate congruent segments in a diagram or figure. For example, in the following figures, a single tick mark is used to show that these two line segments are congruent. If multiple segments need to be labeled as congruent, then we can use double or triple tick marks. For example, double tick marks are used to show that these line segments are congruent, and triple tick marks are used to show that these line segments are congruent. Alright, and this is the basics of measuring line segments. We can find the length of a line segment by using a ruler with an appropriate unit, or we can use a number line and find the absolute difference of the segment's endpoint coordinates. We can also identify and label congruent segments by using tick marks in a diagram, or by using the congruence symbol, which tells us that two line segments have the same length. In our next video, we will go over simple examples that makes use of the concepts learned so far. Measurement of segments, Level 2. In this video, we will start taking a look at simple examples that require us to find the length of segments and use the concept of congruent segments. Before we start, a word of caution. From this point on, I will be assuming that you are very well versed with the basic concepts and skills learned in a typical Algebra 1 or beginning algebra course. You should be comfortable solving equations with a single variable, solving systems of equations with two variables, working with fractions and decimals, and translating word problems into equations. If you're a bit rusty, I recommend you brush up on these skills before proceeding. With that said, let's go ahead and take a look at the first example. Name 3 segments congruent to segment PQ. In this problem, we are provided with a number line that contains various points. Each point has a particular coordinate. We are asked to name 3 segments that are congruent to segment PQ. Recall that congruent segments have the same length. We first need to figure out the measurement of segment PQ before we determine which other segments are congruent to this segment. The coordinate of point P and point Q is -2 and -1 respectively. Taking the absolute difference of both coordinates and simplifying, we obtain 1 for the length of segment PQ. Now that we know the length of segment PQ, let's go ahead and find 3 other line segments that have the same length. One line segment that has a length equal to 1 would be line segment QR. Another one would be line segment RS, and the last one would be line segment ST. So these three line segments would be congruent to segment PQ. Alright, let's try the next example. The given numbers are the coordinates of 2 points on a number line. State the distance between the points, -2 and +6. In this problem, we are given the coordinates of 2 points, and we are asked to determine the distance between the points. Notice that in this problem, we are not provided with a diagram or figure. We're going to have to draw it ourselves. So let's go ahead and draw a number line and use point A to represent the point located at the coordinate -2, and use point B to represent the coordinate located at +6. Now that we have this visual as a guide, we can go ahead and find the length between point A and point B. Similar to the previous problem, we go ahead and find the absolute difference between the points' coordinates. Doing that and simplifying, we obtain 8 as our answer. Notice that in some geometry problems, you will be responsible for drawing the diagram of the problem. At times, you can get away with not drawing the diagram. I personally do not recommend it. Okay, let's try the next problem. Name each of the following. The point on ray DA whose distance from point D is 2. Here we are provided with a number line that includes various points. We are asked to name the point on ray DA whose distance from point D is 2. Let's start by drawing ray DA. Next, we need to determine the point that is 2 units away from point D. Starting from point D and moving in the same direction as ray DA, we see that point B is 2 units away from point D. So point B is our final answer. Let's try the next problem. The point on ray DG whose distance from D is 2. Similar to the previous problem, we want to determine the point whose distance is 2 units away from point D and is located on ray DG. So we start from point D and move in the direction of ray DG. We see that point F is 2 units away from point D. So point F is our final answer. Let's take a look at the next example. 2 points whose distance from point E is 2. Now we need to determine which 2 points are 2 units away from point E. Since we can only move either left or right in a number line, all we need to do is to find the points that are 2 units away from both directions. Starting at point E and moving 2 units to the left, we see that point C is located 2 units away from point E. In the same manner, starting from point E and moving 2 units to the right, we see that point G is located 2 units away from point E. So point C and point G is our final answer. Let's move along to the next example. A segment congruent to segment AF. Now we need to determine which segment is congruent to segment AF. First, let's determine the length of segment AF. So we take the coordinates of point A and point F and use them to compute the length. Taking the absolute value of the difference of these coordinates and simplifying, we obtain 5. Now we need to find a line segment that also has a length of 5. Notice that the only way to get another line segment with a length of 5 is by moving segment AF 1 unit to the right. This new line segment has point B and point G as endpoints. So a line segment that is congruent to segment AF is segment BG. So this is our final answer. Alright, let's try the next example. In the figure shown below, find the following. The length of segment PQ. In this problem, we are provided with a partially labeled number line, and we are asked to find the length of segment PQ. We can easily determine the length by finding the distance between point P and point Q. Recall that we can determine this in a couple of ways. We can use the number line to count the distance from one endpoint to the other endpoint. We can also find the absolute difference between each of the points' coordinates. Regardless of how we decide to find the length, the measurement of segment PQ is equal to 5. Let's go over the final example. If point R's coordinate is 7, why is line segment PQ not congruent to line segment QR? The next problem is asking us to explain why line segment PQ is not congruent to line segment QR when the coordinate of point R is equal to 7. Recall that two line segments are considered to be congruent if they have the same length or measurement. We know from the previous problem that the length of line segment PQ is equal to 5. Let's go ahead and find the length of line segment QR by using the coordinates of the endpoints. Finding the length and simplifying, we obtain 4 for the length of segment QR. Since the length of both line segments are not the same, we can conclude that segment PQ is not congruent to segment QR. We can denote this symbolically by using the congruent symbol with the / going across it. This is similar to the does not equal symbol introduced in your beginning algebra course. Alright, in our next video, we will go over slightly more challenging examples. Measurement of segments, Level 3. In this video, we will go over 2 additional examples that involve congruent segments. Let's jump straight into the first example. According to the diagram, which 2 segments are congruent? In this problem, we are provided with 2 figures. In this case, we have 2 triangles. We are asked to determine which 2 segments are congruent to one another. Recall that 2 segments are congruent if they have the same length. Unfortunately, we do not know the lengths of any of the segments shown in the figure, but we do have tick marks. Remember that we can visually show that 2 line segments are congruent by using tick marks. In the first triangle, segment AB has a double tick mark, and segment BC has a single tick mark. In the second triangle, segment RT has a single tick mark, and segment ST has a triple tick mark. Segments that have matching tick marks are congruent, so segment BC is congruent to segment RT. And this is our final answer. Alright, that was a nice warm-up. Let's try a more challenging problem. The perimeter of rectangle ABCD is 66, and line segment DC is twice as long as line segment CB. How long is line segment AB? In this problem, we have a rectangle that is formed by 4 vertices and 4 line segments. This type of figure is a special type of quadrilateral. Quadrilaterals will be discussed in greater detail in a much later video. For now, we want to determine the length of segment AB, given the fact that the perimeter, the distance around the figure, is 66, and line segment DC is twice as long as line segment CB. We can determine the length of line segment AB by relating the facts of the problem with the geometric relations of the figure. We will have to use algebra in order to set up an equation and solve for the unknown length. In this case, our unknown will be line segment AB. From the figure shown, we know that line segment AD and line segment BC are congruent because both segments have matching single tick marks. In the same manner, line segment DC and line segment AB are congruent because both segments have matching double tick marks. Recall that when 2 line segments are congruent, they have the same length or have the same measurement. Now that we have this information, let's take a look at the facts of the problem and use algebra to set up an equation. We know that the perimeter is equal to 66. This means that if we were to add all the line segments, it should equal to 66. In order to solve an equation, we need to determine our unknowns and assign variables to these unknowns. Since line segment AD and line segment BC are congruent, we can use the variable x to represent their length. Similarly, we can use the variable y to represent the length of segment DC and segment AB, substituting these variables into our perimeter equation and simplifying, we obtain the following. Notice that we have two variables in our equation. In its current form, we cannot solve for any of the variables. We need to replace one of the variables, either x or y, with an expression that will simplify the equation with two variables into an equation with a single variable. We can do just that by using the second fact of the problem. In this case, line segment DC is twice as long as line segment CB. We can express this relation as follows. From here, we can replace the length of segment DC with the variable y and the length of segment CB with the variable x. Now we can substitute this expression for y in the perimeter equation as follows. From here, it is just a matter of simplifying the expression and solving for x. In the end, we obtain x is equal to 11. Now, we are not done yet. This is not like your algebra class, where the goal was to solve for x. In a geometry problem, we need to make sure that we answer the question completely. Notice that x represents the length of line segment AD, or BC. We were asked to find the length of line segment AB, and not the other two segments. So we know from the facts that segment DC is twice the length of segment CB. Since the length of line segment BC is 11, then the length of line segment AB is equal to twice this number, in this case, 22. So this is our final answer. Alright, in our final video on measurement of segments, we will go over two challenging examples. Measurement of segments, Level 4. In this last video on measurement of segments, we will go over two challenging examples involving congruent segments and plenty of algebra to solve. Let's go ahead and try the first example. The perimeter of PRST is 10 more than 5 times the length of segment RS. If the length of segment PR equals 26, find the length of segment RS. In this problem, we are provided with a figure that has 4 line segments. We are asked to determine the length of segment RS. Notice that the figure contains 2 line segments with matching single tick marks and 2 line segments with matching double tick marks. These marks tell us that line segment TS is congruent to line segment PR, and that line segment PT is congruent to line segment RS. We are also told that the perimeter of the figure is 10 more than 5 times the length of segment RS. We can translate this fact into an equation as the perimeter equals 10 plus 5 times the length of segment RS. We are also told that the length of segment PR is 26. This means that the length of segment TS is also 26, since both line segments are congruent. Next, we need to determine what our unknowns are. In this case, we are trying to find the length of line segment RS, so we will represent this length with a variable x. Since line segment PT is congruent to this segment, we can also represent the length of segment PT with a variable x. Now it is just a matter of finding a variable expression representing the perimeter of the figure. In this case, the perimeter will be equal to the sum of the lengths of all 4 line segments. Now that we have this relation, let's substitute the numerical and variable expression for each line segment. Then, we simplify the expression by collecting like terms. Doing that, we obtain the following variable expression for the perimeter. The last step is to set the variable expression representing the perimeter of the figure equal to 10 plus 5 times the length of segment RS. Recall that the length of segment RS can be denoted with the variable x. From here, it is just a matter of solving for x. Doing that, we obtain x equals 14. And this is the length of segment RS. It is important to use geometric relations and algebra together when solving many of the problems that you will encounter in this course. This is why it is important to understand both the geometric concepts and that you are well versed with algebra. Alright, let's end the video with a final example. Given that line segment AD is congruent to line segment CB, line segment AC is congruent to line segment DB, the length of segment DB is equal to 2r plus 5, the length of segment AD is equal to 3m plus 7, the length of segment AC is equal to 3 1/2 r plus 2, and the length of segment CB is equal to 4.2 m plus 5. Solve for the variables r and m. In this problem, we are provided with a figure that contains various line segments. We are also given various geometric and algebraic relations. We need to use these relations to solve for the variable r and m. Let's first take a look at the geometric relations. We know that line segment AD is congruent to line segment CB, so let's draw single tick marks on these segments on the figure shown. We also know that line segment AC is congruent to line segment DB, so let's draw double tick marks on these segments. Now that we can visually see which segments are congruent, let's figure out a way to solve for the variables r and m. We know from the given information that segment AD is congruent to segment CB. This means that their lengths are equal. In other words, the measurement of segment AD is equal to the measurement of segment CB. Since we have an algebraic expression for the length of each segment, let's go ahead and set these algebraic expressions equal to one another. Notice that we now have an equation with a single variable m. So we go ahead and solve for m. Solving for m, we obtain 5/3. We now do the same for segment AC and segment DB. Equating the algebraic expressions and solving for r, we obtain 2. So r equals 2 and m equals 5/3. It is important to set up the geometric relations by using the information given in the problem. Once this is done, it is just a matter of using those relations to solve for the unknown variables. Alright, and this ends the measurement of segments series. In our next series of videos, we will focus on measurement of angles.